All right, welcome. Today we're going to dive into a question that sounds so simple. You probably asked it as a kid, but the answer is just beautiful. We're going to decode the hidden language of color.
I mean, seriously, have you ever just stopped and thought about it? We're surrounded by all this color, but what's actually going on down at the molecular level that makes it happen? It's this incredible mystery, and the biggest clue is something that's all around us, all the time: light. And there it is. That's the secret. You see, color isn't something an object has, not in the way it has weight. Nope. It's the result of this amazing little dance that happens between light and the molecules that make up an object. So, how in the world do we watch this molecular dance? Well, scientists have this incredible tool called UV visible spectroscopy. Just think of it like a pair of superpowered glasses that lets us see exactly how molecules are playing with light. It is the perfect detective kit for solving this whole color mystery.
The way it works is actually pretty straightforward. First, you take a beam of light, one that has all the colors of the rainbow packed into it, and you shine it through your sample. As that light travels through, the molecules inside get all excited, and they literally eat up very specific colors of light. And then finally, a detector on the other side measures what's left over, the light that made it all the way through.
And this right here is the mind-bending part. The color that we see isn't the light the object absorbs. It's the light it rejects. It's what's left over. So a leaf absorbs red and blue light, which means the leftover green light bounces off and hits our eyes. So what's missing is actually what tells the whole story.
Okay, so if molecules are absorbing light, what part of the molecule is actually doing all the heavy lifting? It's time to meet the main character in our story, the star of the show, something called a chromophore.
The name itself is so cool, it literally means color bearer. A chromophore is just a specific arrangement of atoms inside a molecule that's perfectly built to get excited and absorb light energy. You can almost think of it like the molecule has its own little antenna, and it's tuned to a very specific frequency of light. And these little antennas aren't made of anything super exotic. They're usually just common structures, like double bonds between atoms, or these cool hexagonal things called benzene rings that you see everywhere in chemistry. And here's the key. The more of these you can link together in a molecule, the better and better it gets at absorbing light. But you know, our star, the chromophore, almost never works alone. It's got a sidekick, an accomplice, that can't create color by itself, but has a huge impact on the final show. Let's meet the oxochrome. Okay, so an oxochrome is basically like a tuning knob. It latches onto the chromophore and totally changes how it absorbs light. It can make a color way deeper, much more intense. It can even shift the color a little. It's the difference between, say, a pale yellow and a really deep, vibrant gold. And just like the chromophores, these helpers are also made of really simple, common groups of atoms. Things like hydroxyl or amino groups. By themselves, totally colorless, boring. But you attach one to a molecule that already has a chromophore, and boom, the whole system changes, and the color we see gets a serious upgrade.
So let's just put it all together here, nice and simple. The chromophore is our star player. It's the reason we have any color at all. The oxochrome, that's the crucial supporting actor. Can't create color on its own, but it makes the star's performance, that final color, so much richer and more powerful.
I absolutely love this way of thinking about it. One gives you color, period. The other is what gives you the specific shade of that color. It's this beautiful partnership that creates the entire amazing spectrum of colors we see all around us.
Okay, so this is all fantastic for understanding things that, already have color. But what about pretty much everything else? This is where spectroscopy goes from being cool to being a legitimate scientific superpower.
Now, get ready for this because this number is just wild. To our own eyes, more than 99% of the molecular world is completely invisible. We are only seeing a tiny, tiny slice of what is actually there. And that is where the UV part of UV visible spectroscopy comes in to save the day. See, a lot of those colorless molecules, they still have chromophores, but those antennas are tuned to absorb light we can't see, invisible, ultraviolet light. But the machine sees it just fine. And that allows scientists to see and measure all sorts of things that are invisible to us, like DNA or proteins or tiny pollutants in a glass of water. So that really brings us to the big idea. We started with a simple question about carrots and leaves, and we ended up with a tool that lets us see a whole invisible world. It really makes you wonder, right? If we can learn to use light to see the building blocks of color, what else is out there that we can learn to see? What other invisible languages are just waiting for us to figure out how to listen?